And the next talk is on Zoom by Fedele Lizzi. He's going to tell us about quantum space-time, non-commutative geometry, and observers.
Okay, I trust you can hear me, otherwise somebody would tell me something. And so this
We
is...
can hear you.
Okay. That's the title of my talk, and I will talk about things with collaboration with several people in not all together in the same paper, but in the various combinations. And my affiliations is, of course, the official one, and that there is the affiliation which I will bring with me always, which is room 316 in the physics building. And okay. So everyone starts with thanking the organizers, and of course I thank the organizers. I'm very sorry I'm not able to be there in person, and but I had another acknowledgement, which is actually taken from 1985 in my doctoral thesis. I was looking at it for some reason some time ago, and I found this acknowledgement. And I read it because after 5 years in Syracuse, there are many people I would like to thank. And the first one is Balachandran, a Professor A.P. Balachandran. And he taught me the most of what I know, and reproached me for not studying most of what I don't know and I should know. And he showed me how to work and gave me the honor of to be one of his collaborators and friends. Thanks, Bal. Now, this was written in 85, and in 26, I will retire, and if I were to write a retirement thesis, it would be the same acknowledgement with the same. I wouldn't change a single word. So, of course, unfortunately, I would have to change the 5 in 46, and I would change Syracuse in Oxford, Trieste, Naples, and Barcelona. But the first and foremost, I would keep. So, I think it's fitting to start this with this. For some reason, the arrows don't work, and I will have to go with the mouse. Okay, so now I'll start with a preamble, which is probably pleonastic in this audience. Gravity is the theory of curved space-time, and in order to quantize, I can quantize G mu nu, but this doesn't work very well. Nothing works very well. And the idea behind non-commutative geometry, and it's quite fitting that this talk comes after the one of Bishwait, is somewhat complementary to it, and it overlaps a lot with the talk I gave in Kolkata. It looks like yesterday, but there was the pandemic in between. I think it was 4 or 5 years ago, and it's just I will repeat part of the talk and then go ahead. And so we need some quantum space-time, and there are several people in the audience and several people that talk with who have been working on this quantization of space-time. Okay, one way to quantize space-time is to take coordinates which do not commute, and Doppler, Fredenhagen, Roberts have been working in this case, the somehow simplest one. This is a replica of H of quantum mechanics. Just change H bar with theta and make this, and the X with X and P, and make this. But this doesn't have Lorentz invariance and maintains translation invariance. Of course, this is not a problem in quantum mechanics because we have a symmetry which rotates. We don't have a symmetry which rotates coordinates into momenta. So this, I'm going fast on this because several people have been giving similar talks, but the importance of symmetries is quite important. And one way to do is to work with some concommutative space, a quantum space, which has a quantum symmetry. And now, in partial answer to, I think it was Kumar, a question, I call quantum something which is described by non-commutativity. So quantum for me might be also when H bar is 0. And ideally, and I've written recently a paper, you can have cases in which the non-commutative of space and non-commutative of space-time are present. But for this talk, when I call quantum, is anything which has non-commutativity in it. So it's a matter of, it's a definition. Okay, so we need quantum symmetries, and I'm going fast on this because I want to go slower on novelties. So one way is to have a kappa Minkowski. A kappa Minkowski comes as the homogeneous space of kappa Poincaré, which is a deformation of the Poincaré group, which actually was done before kappa Minkowski. And kappa Minkowski is described by this non-commutativity. Later on, I will, okay, this is the time-like kappa Minkowski, the one that also Bijwait was describing. There are other versions, like the null version. I worked on this with Fabio Mercati, but I will not discuss it. And later on, I will have a variation of this theme, which we call Rho Minkowski, and I will describe this later on. Now, as I said, for me, a quantum space is a space in which coordinates don't commute, and I will use the usual techniques of quantum mechanics, and I will remind you, I'm sure you know it. If you don't know it, you, of course, are not able to follow this seminar, but I want to give you a perspective on a quantum space. So starting with the most famous quantum space, which is quantum space of a particle, quantum particle. So I start with a classical six-dimensional space-times, which is described by the 6 coordinates, or 3 times n, if I have different number of coordinates or more particles. But the important bit is this non-commutation relation. And I represent this, of course, as operators. And usually I represent them as operators on L2 or R3. Now, I start with a 6-dimensional space, and I have a smaller number of, this is 6 and this is 3. But I need these 3s because I have a complete set of observables, which are 3. And usually this is the representation that I use. Q is a multiplicative operator, and P is a derivative, and the scale appears here. Okay, Q and P are self-adjoint unbounded operators, and the spectrum of them is the real line for each of the I. And they don't have eigenvectors, they have improper eigenfunctions, they are distributions. We know how to deal with them. Since the QI commute, it's possible to have simultaneous improper eigenfunctions of them, and they are the delta Dirac, delta distribution, delta functions. So for a particular vector, and this is a point in R3, and but then if I want to look at momentum, for a particular momentum P, I have plane waves. And I have this formal eigenvalue equation. How do I find this? Well, I have this formal eigenvalue equation, and there is an IH bar here, which I am will go into the alpha. So this is the formal eigenvalue equation, and I know that there is no solution of this, but I know that there are distributions, and if I require P to be self-adjoint, and the domain of the function to be absolutely continuous function, so I enlarge also a little bit, this is the domain of self-adjointness, I know that alpha must be pure imaginary, because the distribution must be well-defined on the well behaved at the limits in plus and minus infinity. So you know this, and there is an IH bar here missing. And so this you have learned several years ago. Now, improper eigenfunctions are infinite plane waves of a particular frequency, and since plane waves are not vectors of the Hilbert space, there is no quantum state which would give us a measure exactly the values h bar k. Nevertheless, we know how to deal with this. We do wave packets and everything. Now, what I've done here by writing e to the I, q, the plane waves, and I've chosen qi, the three qi as a complete set of observables. That's why I'm representing on L2 over 3. And because I need 3 quantum number. And of course, the psi of q is the density probability of the particles. Psi is complex and contains information about the density probability of momentum operator. This is another important thing. You cannot do quantum mechanics with real wave functions. Wigner, Beppe Marmo would talk about this for a long time, but that's the way it is. There are profound reasons for this. Of course, you know that we could have chosen P as a complete set of observables, and if we choose P as a complete set of observable, then I do a Fourier transform. So I basically Fourier transform the functions from functions of P to functions of Q to functions of P, and everything is dual in this case because the Fourier transform is somehow symmetric transform, and I transform are very symmetric. There is a sign that changes in the nucleus. But I could choose other complete sets, for example, the number operator, angular moment, the 3 number operators, or I can choose the Hamiltonian of the harmonic oscillator, LZ, and the square of angular momentum, everything. So all this we know fairly well. No one understands it, as Feynman said, but we know. Now, if I have a different observer, he will have his own Hilbert space, and he will have his own set of observable and so on. So if I have observers, I have a tensor product. Now, this is not a problem, of course. No one thinks much about this thing, because we can have unitary transformations, very simple, from one set observer to another one. But I remind you that there is a coproduct in this way. So I have to put together representations. Now, quantum groups have taught us that there is more than just the Lie algebra structure. A symmetry is really a Hopf algebra. So I have to put together representation. And usually this is done in a co-commutative way. So I put representation in a let me say, trivial way, and we don't even notice it. But in a deformation of the algebra, if the Lie algebra is deformed, also the group is deformed. Also the way I put together transformation is deformed. And Bishwait was showing cases of this kind. So let me briefly say what a Hopf algebra has in addition to a Lie algebra. So it's an algebra, it's a set which has 2 operators, sum and Lie bracket in this case, and the set of functions is another example of an algebra, in which in this case is multiplication, it's not the Lie bracket. And the functions are associative. The Lie algebra is not associative, but it has Jacobi identity. Now, while a product is a map from 2 elements of the algebra into a single element, the coproduct tells how to put together representation. Formally, it is a map from 1 copy of the algebra into the tensor product. So this is the fairly trivial and common example, and that's how I put together 2 representations. And this is basically the Leibniz rule. So if the Lie algebra I represent as differential operators of the first order, this is how I act on products. This instead is another coproduct of the co-commutative way, the simple ones. And this is what happens if I make multiplication of functions, because if I have functions on a group, this is the way in which I multiply the functions on the group, pointwise multiplication. There are 2 more structures, co-unit and antipode, which are dual to unity and the inverse. And they are important, but they are not relevant for this seminar, so I will not remind or describe them. Okay, earlier we discussed, there is a D missing here, quantum phase space, where the deformation parameter was h bar. And now I want to reproduce this discussion for Kappa-Minkowski. Okay, now our 4-dimensional space has different commutations. It's a four-dimensional, as I said, and the deformation parameter is lambda, which is I call lambda 1 over kappa. I think, and for when people did kappa Minkowski, they were thinking it was speed of light. So the classical case was recovered in the limit of the parameter going to infinity. I'm more in the quantum camp, and so I like to have classical limits when the parameter goes to 0. So this is a quantum space in the way I said before, and I will consider its kinematics and leave H bar alone for the moment. For this talk, I said I try to do work also in a paper called double quantization. But this is a relativistic space, so I need to worry about Poincaré transformations. And I will do it in a moment. So I have the representation of the commutation relations, and I want to look at a representation of this non-commuting variable, so there will be operators, on a space. So although the space is four-dimensional, I will have to look here on the Hilbert space of square integral functions on a smaller space. Phase space, I do the same. And the dimension of the space is given by the set of commuting observables. And the set of commuting observables have the xi. So I take this xi to be multiplicative operators, and in this case, time x0 is a dilation operator. It's a dilation operator, then I have to add 3 halves because those two don't commute, and if I don't put 3 halves, this will not be self-adjoint, not even Hermitian. And there is an important thing to notice. I think that this has been noticed not very much by the Kappa-Minkowski community. The Kappa-Minkowski is really natural in radial coordinates. So this is the radial coordinates. And in fact, the best way, in my opinion, to write the Kappa-Minkowski non-commutation rules is the following. Is x0 commutes with every function on theta phi. Of course, theta and phi are not good variables. They are not self-adjoint. I'll discuss this later on. But what the only non-trivial commutation is this one, is x0 r equals I lambda r. So, of course, we didn't discover this, but not many people have noticed it, have used it. And this gives us only Heisenberg uncertainty relation, this one. So there is an uncertainty between x0 and r. I have now reduced the problem to a one-dimensional problem, but it's very important. R is not is one-dimensional, but the measure in integration shouldn't be integral in dr, should be integral in r squared dr. So what's the spectrum of this operator? And I have to do the same thing that I did before, but now, to make a long story short, this is dilations, apart from the 3 halves. Actually, the 3 halves is important. So the monomials are the not the exponentials of imaginary quantities. The monomials with an imaginary exponent are the improper eigenfunctions, and in fact those are the distributions, the improper distributions. Notice that there is r to the I tau, but then there is a r to the minus 3 halves. This is coming from here. This is very important because when I integrate, I think I said it later. No, I don't say it. If I integrate this monomial, I have to put an r squared in the measure. Therefore, this becomes r to the 1/2. Now, r to the 1/2 diverges on both ends of the spectrum, diverges in 0 and infinity, but diverges just about. It's the same that happens with plane waves. Plane waves at plus and minus infinity, the integral diverges because it doesn't go to 0 either way, but it just about. So it doesn't diverge brutally. So this is the same thing. In fact, is the key to these Mellin transformations. Quantum phase space were connected by a Fourier transform, and Kappa-Minkowski, I can have two sets of observables. R theta and phi, it's an abuse calling R theta and phi, so R and then functions and theta and phi, but I have another set of commuting observables, which is tau theta and phi, and I can have functions which are functions of R theta and phi, but dually I can have functions which are functions of tau theta and phi, and the two of them are connected by a Mellin transformations in 3 dimensions. The measure is important. The Mellin transformation would have integral in the R, but here there are measures coming everywhere. And I can interpret this psi modulus squared and tilde psi modulus squared as the probability density to find the particle in the position R or tau, respectively. So now it's good to have an idea of the dimensional quantities which are involved. If I call T the eigenvalue of the time operator, this is x0 divided by c, the speed of light, then tau is Tc divided by lambda. So d divided by lambda is a dimensional quantity. And this dimensional quantity is the dimension of a frequency, of the inverse of a time. And if I choose for lambda the Planck length, then this is 10 to the 43 hertz. So if t equals 1, then this tau, so t is 1 in a second, then tau is 2 times 10 to the 43, which is an extremely large number. But if t, say the time is of the order of the Planck time, then tau will be 1. So keep this in mind. This tau is a small, the eigenvalue is a small number only if time is Planckian. Now I can try, I have to localize states. So in usual quantum mechanics, I localize states in a Gaussian. Here Mellin transforms and something, and I have choose to localize a state in this conical section. This is just because the calculations become easier. There is nothing mysterious in this. So I take this this localization in a section which has an angle of which is of the order of 2a divided by lambda, and a is the thickness of this. And if I take the limit of a going to 0, so the thickness going to 0, and automatically the angle closes, and then I have a localization in a point around the z-axis. I choose the z-axis just for. So this is the formula, but the picture is more. So I'm trying to localize this state in space at a distance z0 from the origin. And so what happens if I try to localize in space to the localization in time? And the localization in time, this quantity goes to a constant when a goes to 0. And if the psi dagger squared goes to a constant, the localizing in time means delocalizing in space. In fact, I can see this by doing it's not simple to see from this. It looks like it goes to 0, but I have to make a series expansion of this for a around 0 and z0 around infinity, because I want to be distant from the origin. And I see the same thing, that the two Taylor expansions are the same, a and z0, a and 1 divided by z0 go together. So what does this mean? That if I sharply localize a particle far away from the origin, it means that the particle cannot be localized in time. And this is the uncertainty of Kappa-Minkowski that I described it, which was here. Okay, so if I try to, I cannot localize both of them at the same time. I can only if R is small. Okay. As I said, only if R is small. I can localize at the origin. The origin becomes an exceptional point, becomes a point in which I can localize states. Now can do the same with log Gaussians and find the same thing. I will skip this. Okay, because of time, I will skip this, but I can localize now with the Gaussians, and the dual one are of the log Gaussians in space are Gaussians in time, and so there is this localization. Let me go. I realize I'm going because I want to do the variations as well. Okay, this is, I can do the double limiting, which are 0. Okay, this is, okay, sorry. I'm doing shortcuts, but I don't know if I'm missing something important. Okay, localization is at the origin at time t equals 0, but I can also localize at an arbitrary time, and this I can multiply the original state by this phase. This is a phase r to the it 0, and I call these states O tau, which means that I localize at some along the origin at some time. So now let me tackle this problem. I organized the origin as special point. So there is a point in the universe which is the origin, the place where the Kappa god, let me add another god to the pantheon, Indian pantheon. No, there isn't a special point in Kappa-Minkowski. That's what I argue. When I talk of the states, I assume the existence of an observer measuring the localization of states. This observer is located at origin, and for him, here and now makes sense. She cannot localize. I've decided to be gender fluid because I hate the stars and things like that. So I'm gender fluid. The observer changes gender throughout the experiment. So the observer cannot localize with precision states away from him as a consequence of the non-commutativity of Kappa-Minkowski. So this is the point. So I can localize where I am, my states are. What about other observer? And now this is a very good example because I'm doing a remote talk. In order to have a different observer, I have to translate state and boost. Usually these are done with an element of the group, the Poincaré group, but now I have Kappa Poincaré. Now, what in Kappa Poincaré, there is a tensor product because X going to X prime as the lambda. As I have to combine a transformation in the Poincaré group plus a mu. But now this lambda and this A don't commute. And in a particular basis, this is their commutation relation. Notice as Bijoy was commenting already, the lambdas are still commutative, but the commutator between the A's and the rotations of the A's or Lorentz transformation of the A's, but now the translations are not commuting. And what happens is an algebra observer, but I've chosen an observer, it's an algebra operators, but I've chosen an observer. The observer himself is a quantum object. And therefore, I will be described by some functions, but the functions of this A mu don't commute, and they have the same non-commutation relations as the x's. Therefore, in translating, I have an uncertainty in the translation. I have a very good example of this. Here I have a pen in my hand. So you don't know exactly where I am. You know that I'm in Naples, that I'm in Italy, and you have a fair idea, if you know geography, of where I am now that I'm talking. And well, I've been to Kolkata, but let's say that I have a fairly good idea where you are, where Sachin is. And I've seen Sachin recently near a podium. Now, you know that I am near this pen. And therefore, you know that I can localize this pen very well. And I know that Sachin is near that podium. So I know that Sachin can localize this podium well. But you cannot localize this pen just because you don't know where I am. So this pen is not is not very well localized with you in Kappa-Minkowski space because it's far away from you, but you have no problems in knowing that it's near me. Now, we are in a classical world. So if I send you the GPS coordinates, you can localize me and the pen exactly. Also, the fact that it's slightly farther from my nose, if I send you a very precise coordinates. In quantum space-time, I cannot do this. And this is in words what I said in what I say here. And there are various aspects which can be described. But the important thing is that the observer is a quantum object. Quantum observers, in fact, subsequent papers that I've written, quantum observer in the title. I think this is an important thing. If one is doing quantum gravity, the observer has to become a quantum object. And this means that I cannot sharply localize observers. They will be described by functions, and I can explore this space observer, which is, again, states on an algebra. So I can define the identity transformation. So two observers which are nearby, and they are related by the co-unit. Fortunately, in Kappa-Minkowski, this co-unit is trivial, and therefore is in this representation of Kappa-Minkowski, which I'm using, two observers nearby will agree. This is not totally trivial. In Moyal case, this can be actually different if the two observers are rotated. Another thing is that since Lorentz transformations are commuting, we agree in directions. So rotations are not a problem. So the directions up of this pen, everybody would agree, is the localization along R. So coincident observers are well defined, and I can, in order to change observer, a change of observer transforms the x's, and the x's and x prime correspond to different observer. This one is actually, there is implicit a tensor product times the one time is the identity times x prime equals to this. And therefore, I have the same, I have to transform using the coproduct, which is non-trivial. And I cannot sharply localize position. I can not localize observers. That's what the change of the symmetry is telling us. But as I said before, since Lorentz transformation commute, I have no problem there. Okay, I can have the action of, I'm running out of time, action of the, see how in 1 + 1 dimension, I can actually, which is simpler, I can actually have a representation of this, all these objects with a relatively simple non-commutation relation. The Lorentz transformations are given just by rapidity. There are only boosts. And I can actually find the representation of the translations and time translation and space translation, and they have this formula. And I can use, and I can actually verify how things go. States will be objects of this kind. We'll have tensor product. I could have entangled states. We haven't studied them in detail, but they will be something which in the observer space and something in the configuration space, and I can translate things. Now, the expectation value of the transformed coordinates is completely defined by translations. Translations are simple because two different observers are comparing position and not directions. As I say, the directions don't create any problem. I can have expectation values of objects, and here there is, I want to just stress the fact that
Fedele, you have 5 minutes.
Yes, in fact, that's why I'm running. I'm running fast. All the uncertainty are when I transform, I increase uncertainty. So if I have a chain of transformation, the state sort of gets degraded in the knowledge. Okay, this is, I said in words, this is ideally, ideologically, say, compatible with the relative localization, is Kowalski, Amelino, Fedele, and Smolin, but the context is different. So we don't consider momentum space, or we don't have curved momentum space. It will be interesting to understand better. Okay, I will now very quickly describe in 4 minutes a variation, because this is really a novelty with respect to talks I have already given. Let me discuss this Rho-Minkowski. Rho-Minkowski is a variation of Kappa-Minkowski. You can see that the algebra is time with x1 gives x2. So this is a rotation. This is a commutative space, and this is a rotation. So this has a long history. There are several names here. And I have variations also on this theme. But so this is, the group is, now in this case, the ideal coordinates are the following, the cylindrical one. So T, rho, Z, and phi. And let me write in inverted comma the commutation relations. I know that phi is not a good variable. A better expression is this one. So the non-commutativity is between time and the angle. And phi, the angle in cylindrical coordinates, or phi, actually is the same as the polar coordinates. Okay, I have to resist the temptation of write delta t, delta phi, because this is a question that is asked in exams in quantum mechanics. But I know how to deal with this non-commutation relation, because this is the non-commutation relation of LZ. And the thing is that this operator has a discrete spectrum. Now, it has a discrete spectrum. So time is discrete, and a change of basis is given by Fourier series. And so this is the delta. And if I, after a time measurement, I just collapse into a time. Again, an idea of numbers. The chronon, the unit of time, is very small. And if I want to have a localized space, now, if I want to, the most accurate 10 to time is 10 to the 19, and this is a superposition of 10 to the 35 quanta of time. So this is the approximate Dirichlet function. And already when I go to 10 to 15, this is fairly localized. 10 to the 35 will be much more localized. And I want to finish by saying again, so I have a clock which scans the universe. Again, no, because the choice which I make is a choice of time, but I know that there are several self-adjoint extensions of this operator, the momentum on the circle. And therefore, any observer will have its own time, but different observers have different origins. And so there isn't a universal clock. There are observers which have discretized time. And okay, this I'll skip. We studied this non-commutativity with the Serbian group, Maria Dimitrijevic and Nikola Konjik and other people, and there are several papers which I have no time to discuss. Let me, I think a couple of minutes, yes, exactly 1 minute and 4 seconds, and the final remarks, but they have a postscript. And the main message I want to convey is that there is quantum space-time, and quantum space-time will require quantum observer. And this is true for quantum space and quantum phase space as well, and this is the challenge. I promised a postscriptum. The postscriptum in the 30 seconds which last are the rest of the acknowledgement of my thesis. And I decided to put it here because this is a way to remember old friends and to remember what for me is the most formative period of my life, which were the years in Syracuse. Some of the friends are not here anymore. So I was thanking Carl Rosenzweig, and I was thanking colleagues Gianni Sparano, and that with whom I shared a discussion of physics and few Grand Cru. Grand Cru are the best wines from Bordeaux. I was there with Nair, Rajiv, Al Stern, and they are still around. And some people I lost, like Track, I have no idea what they do, Harald Gom. Some people we lost because Kamesh and Omer Kamachalan are not anymore with us. And okay, this is the rest. I thanking places where I was, including this was the Eastern Music Festival because I was dating a cellist at the time, and I was tongue-in-cheekly, part of the thesis was written when I was visiting her at this Eastern Music Festival. But as I said, for other reasons, I looked at this thesis and not long ago, a month ago or something like that. And I think it's fitting to remember what for me and for the people named here and the students that came before and after, what has been, I think for all of us, one of the most important periods of our life. And this has been the years that we spent with Bal as students. Okay, thank you very much. And this is those of you that were in Syracuse will recognize the modern version of this room. Okay, thank you.
Thank you, Fedele, for a very clear talk. We should open the floor to questions.
Hello, Fedele. Annesha here. So probably you have answered my first question, but you were very quick in that slide. So I want to verify that the concept of localization and the localization of a point with respect to different observers, which you just discussed, is it related with the concept of relative locality?
It is ideologically, this is the comment I did. We get to the same conclusion.
Yes.
Namely, that far away things can be not well localized. I claim that we are more rigorous because we do the theory of operator on Hilbert spaces. Localization is a measure, and we are in so in this context, the intuition of Gianni, Jerzy, Laurent, and Lee is more based on the curvature of momentum space. Here we don't have momentum space. The two things are obviously connected, but at a deeper level, which I started to investigate in a paper called Double Quantization, trying to do some non-commutative geometry of quantum space-time. There are problems because time in quantum mechanics is not a good operator. It's not a good, it cannot be seen as an operator. So either one should go to quantum field theory, but even there things are complicated, or should understand the role of time in this in a better way.
Mm-hmm. Okay, and one more question. If I understood correctly, your translation generators are not commuting. Am I right?
Yes.
So
You are right. Their commutation relation is exactly the same as the kappa Poincaré,
yes.
the kappa Minkowski ones. So A0 commutes with everything because they cancel, and A0 AI equals I lambda AI.
Yes. So, in context of this point, so a la Max Born, can you say that the space-time is curved here? So, we know that there is a duality between the curvature of space-time and non-commutativity between the translation generators. So, what is your comment on that in this case?
That I would like to know, to understand it better. This is the key. This is the connection between the 2 points of view. Namely, if you have this, then your momentum space is curved. But we don't use this explicitly, this momentum space curvature, because we don't have momentum space. We don't have momentum here. And now
These are not. You are not identifying these as your momentum.
I don't have momentum in this. I have kinematics. I don't consider momentum in this paper. So of course, this is the parameters when I do the group. This is the parameters of the momentum. So so I don't have a group. Those are the coordinate parameters of the momentum transformation, the e to the I a mu p mu. So, and they don't commute. So since they don't commute, the momentum space is curved. And so this is I think was Jerzy Kowalski-Glisman, the first one that noticed this. I'm not 100% sure, but he was the first one to say this. So if I put momentum in this scheme, the momentum will be curved. And but I do everything without momentum. I'm kinematical basically here. So I'm describing this space-time, and I'm describing observers looking at this space-time. Now, when these observers will start moving and I will put a complete dynamics, then something will happen. I don't even have a Schrödingerish equation in this case.
Okay.
So I'm behind that. And okay, with papers, now there is no time really to comment, but in papers with Flavio Mercati, we were trying to study the momentum space also with this point of view, but there are no complete understanding, let me say, of the connection. So there is a
Question from Bal.
obvious understanding of the fact that there is a connection, but not of this connection. And now comes Bal. And I am again a student and fearing this question. Go ahead, Val.
Ciao, Fedele. There are a couple of things. First is, I don't know how one will do scattering theory in this model.
Which theory? I'm sorry?
In this kind of kind of framework, for scattering, you should have localized wave packets which move in time normally. Here, you can't do that localization because there is because of this non-commutativity of this commutation relations between x and t that is involved here. So I don't quite know what is meant by scattering theory. How will I scatter things in this model? The second question is, unless the momenta translate positions, there is no experimental identification of what is meant by momentum. It is just a symbol in the model. Okay? If you identify positions as the coordinates, as a commutative algebra, you can think of it as a commutative algebra of space-time. But unless the operator which you call momentum translates these positions, there is no way to tell what it is. Because normally, a priori, there is no way, because the way one normally tells it is from exponential I p dot x, okay, that expression. But you can't write that if momenta don't translate positions. So I don't quite know what is meant by momentum here.
Okay, the second question, I agree. The first one,
one more thing. I'm sorry.
Okay.
Beautiful picture of 316. I don't know where you got it from, but it's very nice.
What you send it to me?
With the table and the blackboards, whiteboards.
You send it to me. You sent me two pictures. One with you, because when I was writing, I don't know if the volume is already available, but the volume celebrating you, my contribution is called 316. And I brought to you, and you had Indra take a picture of 316, and so probably Indra sent it to me.
Probably.
You are my connection. There is no one else in Syracuse. Well, I could have asked Carl, but unfortunately, I actually looked at it. I don't have any 316 picture of the 316 I know, the one in 1980, but I will have to do with the new one. The good thing is that 316 is still there, and is there also virtually, because it has been mentioned, the Anwesha talk that she gave in the seminar series of Room 316. Now, it means that there is a locus of the soul which has lasted more than nearly 50 years, because when I arrived in Syracuse in 1980, 316 as a meeting room, or rather than physical room, was already there. So it's a remarkable achievement. I think that the Plato Academia, or the place where the Royal Society was meeting, didn't last 50 years. They probably changed it, but so it's a remarkable achievement. Very quickly, because I'm I'm cutting into your coffee time. Scattering. I thought of scattering. Scattering would be a fascinating thing, because it means that it's very difficult to localize an incoming state, but then the description is different if you are in the center of mass. So the observer is near the scattering, or you are translated from it. And of course, everything has to be done has to be transformed with these translations. I think there would be, so rather than having scattering, just the scattering process pi going to gamma gamma, but the very process of scattering of ultra high energy would be different. So the idea of two particles going and then going away, it wouldn't work if you are at this very high energy. So again, I don't know. But because the in and out state, field theory, also this semi-classical, but in and out state, the definition of in and out state, it's very interesting, because you cannot localize them when you don't know where they're coming from, but you know when they arrive. It's like bad luck. You don't know where it's coming from. It's easily coming. But when it hits you, then you can localize it. Okay.
So I think we are run out of time, but so let's thank Fedele again for a very clear talk.
Okay, you go for coffee. We all go for coffee.